Hello everyone. On this video we will be covering Green's theorem. Alright, so to start off, just kind of a quick description of a simply connected and non-simply connected curve. Okay, so let's say you have a curve that we will call C, of course, given by the vector valued function r of t equals some function of t times the I unit vector plus some function of t times the j unit vector, where you have the boundary between a and b. Okay, and that's defined as a simple curve if it does not cross itself. Okay, so in other words, for some value c and some value d, they're never going to be equal. Okay, for every value of c and d in an open interval. And that open interval will be between, of course, a and b. Okay, now a plane region that, of course, we will call R is simply connected is basically if you have a simple closed curve. So if its boundary consists of one, that's the key phrase there, simple closed curve. All right. Now visually, this is the idea behind it. And clean up that Y a little. There we go. Okay. So if you have a curve that, let's say, looks like this, and of course it's going counterclockwise, and this is your region, this is actually simply connected. Okay. But if you have a curve that, let's say, looks like this, and again it's going counterclockwise, and let's say it has a hole right here, where that's your region. Or let's say if you have one that kind of looks like this, where of course it's going counterclockwise, so it's going like that. These are not simply connected. Okay, so these will slowly lead up to what we will call Green's theorem. All right, so we don't have a whole lot of room on this page, so we're going to go ahead and continue this on the next page. So if you are still writing, feel free to press pause, but we're going to go ahead and write down the definition of Green's theorem. Okay, so Green's theorem. Okay, so if we let our region R be a simply connected region with a piecewise smooth boundary, that of course we will call C. Oriented counterclockwise. All right. So if our M and our N have continuous partial derivatives in an open region, containing R, then your line integral can be solved using a double integral. The partial derivative of n with respect to x minus the partial derivative of m with respect to y, and that's with respect to the area of the region. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move this to the next page to do our example, because I don't think it will all fit on this one. Okay, so what if we wanted to use Green's theorem to evaluate the line integral so you have y minus x dx plus 2x minus y dy. Oh, that's your path. Along the path, C, where C is the boundary of the region lying between the graphs of y equals x and y equals x squared minus x. All right. So with this, it helps to graph the region. So you want to graph those two just to help you visualize it. So when possible, graph the region. All right. So that means we graph the region. This is our x and this is our y. Our y equals x, of course, looks like that. And our y equals x squared minus x actually looks something like this. Okay, so let's see, this is our 1, This, of course, is our 2. This is our 1. That, of course, is our 2. So this is our origin of 0, 0. The point where they intersect is 2, 2. Okay, so really we're looking for the line integral of that region. Okay, so of course this is our y equals x, and this graph is your y equals x squared minus x. Alright, so we can go ahead and start our integration using Green's theorem. So if you have m dx plus n dy, that equals the double integral of the partial derivative of n with respect to x minus the partial derivative of m with respect to y, and that's with respect to the area of the region. Okay, so here, I'll put that right on the side. Of course, let me write that out so I'm not skipping any steps. We have y minus x dx plus 2x minus y dy. This is your f of x, y, so of course this is your m, and that's your n. Okay, so your partial of n with respect to x, okay, that would be seen as a constant, so that would disappear. So you'd be left with just 2. The partial of m with respect to y, for this one here, since that's your m, that would just be 1. Okay, so you can see here that your partial of n with respect to x minus your partial of m with respect to y is just 2 minus 1, which is 1. Okay, so that means this is going to equal the integral, and we'll write our double integrals, we'll fill in our constraints right after. So that would be a 1 dy dx. Okay, we already know our constraints for our dy. That's y equals x, and y equals x squared minus 2. I mean x squared minus x. Alright, so we're going from x squared minus x to x, because we're going from bottom to top. Alright, and for our dx, we can see that our x goes from 0 to 2. That's why drawing it helps, if possible. Alright, so from there, we just go ahead and integrate. Okay, so starting right in the middle, the integral from 0 to 2. So the integral of 1 with respect to y is just y. And that's from x squared minus x all the way to x. And don't forget our dx here. Okay, so if we plug those in, integral from 0 to 2, so it's x minus x squared minus x dx. Okay, so if we go ahead and distribute that negative and combine like terms, we end up with the integral from 0 to 2 of 2x minus x squared with respect to x. Okay, so if we go ahead and integrate both of those, we end up with x squared minus 1/3 x to the third from 0 to 2. Okay, so if we go ahead and plug in our 2, we end up with 4 minus 8 over 3 minus, so we plug in the zeros, of course we get 0. So if we go ahead and solve this, we can make that 12 over 3 minus 8 over 3, which will give us our answer of 4 over 3. All right. Okay, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Alright, so let's say, for example, we want to use Green's theorem to find the work done by the force, and our force will be our vector field. So we have x, y times the I unit vector plus x plus y times the j unit vector on a particle that is moving counterclockwise around a closed path Okay, so our curve will just equal x squared plus y squared equals 4. All right. Okay, so we know our f of x, y is equal to xy times the I unit vector plus x plus y times your j unit vector. Okay, where of course this is your m and this is your n. So that means your partial of n with respect to x, that's going to equal 1. And your partial of m with respect to y, that's going to equal x. All right, so that means our Green's theorem formula is equal to the double integral minus partial of n with respect to x minus partial of m with respect to y with respect to the area. Okay, so our partial of n minus our partial of m is just 1 minus x. So this becomes 1 minus x. So we have our double integral of 1 minus x with respect to the area of the region. Okay. Now if you're going to calculate for work, we have to take into the fact that our region, or the particle rather, is going in a circle. X squared minus y, well, plus y squared is equal to 4. Okay, so since it's going into a circle, of course, it will be a little bit easier to convert this to polar coordinates. Okay, so to find the work done, let x equals r cosine of theta, and y equals r sine of theta. Didn't really need that. Okay, so we know that since our path is a circle, Remember, it's x squared plus y squared equals 4. X squared plus y squared equals 2 squared means that your radius is going to go from 0 to 2. And of course, going in full circle, your theta is going to go from 0 to 2 pi. All right, so now we can go ahead and plug that in. So 1 minus x with respect to the area is equal to the double integral. Okay, you have your f of r theta, which is 1 minus x, which is r cosine theta. So 1 minus r cosine theta. Okay, so you have the f of r theta times r dr d theta. Okay, with respect to r, our radius is from 0 to 2, and our theta is from 0 to 2 pi. All right, so that's going to equal, if we integrate our middle, well, first, before we do that, go ahead and get rid of that r by distributing. So we have from 0 to 2 pi and 0 to 2, you have r minus r squared cosine theta, dr d theta. Okay, so we go ahead and integrate both of those. From 0 to 2 pi, we end up with 1/2 r squared minus 1/3 r to the third cosine theta. And of course, that's from 0 to 2. And don't forget our d theta. Okay, so if we go ahead and plug in 2, we get 4 times 1/2, which is 2. Minus, plug in 2 here, we get 8 over 3 times cosine theta. So if we minus, we plug in 0 to both of those, it just gets 0, so there's no point in putting those in. So now we go ahead and integrate this. So the integral of 2 becomes 2 theta minus 8 over 3. The integral of cosine is sine, so that will be sine of theta. And that's from 0 to 2 pi. So we go ahead and plug in our 2 pi. We end up with 4 pi. Sine of 2 pi is 0. So 4 pi minus 0. If you plug in 0, of course, you get 0 again. I'll go ahead and plug that in. So we end up with 4 pi. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Okay, so let's say, for example, if we wanted to evaluate the line integral and so let's say y to the third dx plus 3x y squared dy, where C is closed and counterclockwise oriented. Okay. Now, if you notice, they didn't give you a whole lot for this one. And there's kind of a reason for it. Okay, so I'm just going to go ahead and rewrite. Oh, didn't write that one. dx plus n dy. Okay, so if we have our integral y to the third dx plus 3x y squared dy, see that the partial of m with respect to y is equal to 3y squared. And the partial of n with respect to x is equal to 3y squared. Of course, this is your m, and this is your n. Okay, well, what does this tell you? Well, it tells you that this is conservative. Okay, now what does it tell you when it's conservative? Well, that tells you that you plug in your m and n, you have your double integral over the region of partial n with respect to x minus partial of m with respect to y, and that's with respect to the area of the region. Okay, so really this just becomes 0. 0, well, 3y squared minus 3y squared is just 0. So really the double integral of 0 is just going to be 0. Okay, so that means when you have a conservative line integral, then your answer is just going to be 3x y squared dy is just going to be 0. Because as soon as you end up with 0 here, it's just going to keep being 0 over and over. So, all right. Okay, so if you're still writing, feel free to press pause. But we're going to go ahead and move on to our next section, which will cover using a line integral to find the area. All right. Okay. So line integral find the area. Okay, so let's say if R is a plane region bounded by a piecewise closed curve C, of course, is oriented counterclockwise, then the area is given by the area is equal to 1/2 times the line integral x dy minus y dx. Okay, which is pretty straightforward. Okay, we'll do a couple of examples and you'll see what I mean by that. But the thing that's not kind of straightforward is having to remember a few things. Okay, so because this will probably come up, if you remember, let's say if you have an ellipse that's elongated horizontally. Okay, so it looks kind of like, well, of course that doesn't look like an ellipse. Kind of straighten it out just a touch. Okay, so this is an ellipse elongated horizontally, or horizontal major axis. Okay, so from your origin to the endpoint, that's your A, and for your minor axis, from the origin to the actual ellipse, that's your B. In the equation, x minus h squared over a squared plus y minus k squared over b squared is equal to 1. Okay. Now, if it's elongated vertically, it's a little bit of a switch up, but not much. Okay, so if you elongate it vertically, and again, it may not look like an ellipse, but you knew before you started watching this video that I cannot draw, so use your imagination. All right, so ellipse elongated vertically, you have x minus h squared over b squared plus y minus k squared over a squared equals 1. Okay, now what does this tell us? This tells us that x will equal a cosine of t, and y will equal b sine of t. Okay. Now remembering this will definitely help out for a couple of your examples. I mean, well, not a couple of your examples, but a couple of your problems. All right, so I'll give you an example of how this will help out. Okay, so if you're still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Okay, so let's say, for example, if we wanted to use the line integral to find the area of the region, okay, let's say R is just your region bounded by the graph x squared plus y squared equals a squared. All right. So what do we know about our region? Well, basically a circle with a radius of a. X squared plus y squared equals r squared. In this case, your r is equal a. Since the region is a circle with the radius equal to a, x is equal to, instead of r cosine theta, that's a cosine of t, not theta. Same thing, y equals a sine t. And since it is a circle, we know that our t has to be between 0 and 2 pi. Okay, now this is where it gets a little bit fun, I guess you could say. We have our x, our y, and our t value from 0 to 2 pi. Now you find your derivative of x. Derivative of cosine is negative sine, so that's negative a sine of t dt using our differentials. And our dy, derivative of sine is cosine, so that's a cosine of t dt. Okay, now we're going to look at our formula to find our area. X dy minus y dx. Okay, so that's going to equal 1/2. Remember, that's from 0 to 2. We have x dy. We have a cosine of t for our x. And our dy is a cosine of t dt. Or just a cosine of t. I'll put the dt on the end. Okay, minus y, which is a sine of t, times dx, which is negative a sine of t. And I'll put the dt right on the outside for both of them. Okay, so if we go ahead and simplify each one of those terms, we have a squared and cosine t squared. So that's a squared cosine squared of t plus, because you have minus and minus gives you plus, a squared times sine t squared. So a squared sine squared of t respect to t. That's equal to 1/2. Okay, again from 0 to 2 pi. If we factor out our a squared, we have a squared times cosine squared of t plus sine squared of t with respect to t. Okay. And we all know that cosine squared plus sine squared is equal to 1. So that's 1/2 the integral from 0 to 2 pi of a squared times 1, which is just a squared with respect to t. All right, so here we can just go ahead and integrate. So that's 1/2 the integral of a squared with respect to t is just a squared times t, and that's from t equals 0 to 2 pi. Okay, so if we plug in 2 pi for our t, we end up with pi a squared. The 2's cancel out. Minus, we plug in the 0, we get 0. So we didn't have to put that, but we end up with pi a squared for our answer. And the a only depends on what the radius is. All right, so this is if you have a circle. If you have an ellipse, that's when the previous remember these came, when I first wrote down, came in handy. So that's when this page comes in handy. You have to remember those. All right, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Okay, so what if we wanted to use a line integral to find the area of the ellipse, say x squared over a squared plus y squared over b squared equals 1. All right, so looking at this, it can tell us one thing. Move back to my other sheet here. That this is elongated horizontally. Okay, so since this is an ellipse, elongated horizontally, and we know it's centered at 0 because it doesn't have the x minus h and y minus k, so those have to be 0, 0. So we know it's centered at the origin. We know that x is equal to a cosine t, y equals b sine of t, and of course for an ellipse, it's still going from 0 to 2 pi. Okay. So once again, we have our x and our y. Our dx is equal to negative a sine of t dt, and our dy is equal to b cosine of t dt. All right, so just like before, we're going to go ahead and plug in our x, our y, our dx, and our dy in our area formula. Okay, so we know that the area is equal to 1/2 times x dy minus y dx. Okay, so that's going to equal 1/2 from 0 to 2 pi, our x dy, so we have a cosine of t, times your dy, which is b cosine of t, put a little bracket there, minus your y, which is b sine of t, times your dx, which is negative a sine of t. And of course, that's all with respect to t. Okay. So again, if we go ahead and combine these, you have a times cosine times b times cosine. It's just a times b times cosine squared. And here you also have a and b that you might as well factor both of those out. So you have a times b times cosine squared plus sine squared. I don't really need that. And that's with respect to t. All right, so just like before, we know that this is going to equal 1. Okay, which means we just integrate 1/2 times AB with respect to t. Okay, so since a and b are constants, we have 1/2 AB times t, and that would be from t equals 0 to 2 pi. Okay, so if we plug in t equals 2 pi, we'll get pi, because of the 1/2 cancel out. So you have, got my equal. Pi times a times b. Of course, we plug in 0, we just get t equals 0, and everything else becomes 0. So that's just pi times a times b. All right. So hopefully this made sense, and I will see you on the next video.